Okay, so this is about calorimetry and heat capacity and specific heat. There are two different ways of determining, of finding the heat of a reaction. There is heat capacity with a capital C and a specific heat with a lowercase s. Okay, and here are the two equations. You notice that Q, which is heat, is for both of them. One is C times delta T, the other is SM, which is mass, times delta T. So the way that you could tell inside a problem is C has the units of joules per degree C or kilojoules per degree C, and S has the units of joules per gram degree C, or again kilojoules per gram degree C. So this one does not take into account the amount of material that's present, and this one does take into account the amount of material that is present. And so other than that, they're basically the same definition. So it's the quantity of heat raised the temperature of a sample 1 degree Celsius, and we are in chapter 6, so we're back to degrees Celsius, versus this one has to raise the temperature 1 gram of substance by 1 degree, okay, at constant pressure. The specific heat of water, this was originally done for calories, so the specific heat was set for 1 calorie per gram degree C. And then to go from calories to joules, it's 4.184 joules per gram degree C. Okay. Here are some of the other specific heats that are, these will all be given to you on the test. Aluminum, copper, of course, are low because they're metals, so they conduct temperature very well. Ethanol and water are non-conducting, okay, and so they're fairly high. And iron is also a metal, so it's low. So of these listed, it's the hardest or takes the most energy to heat water up than it does any of the others listed here. The difference between these two columns, as you see, this is grams and this is moles. If I take this times its molar mass, I would get that. This times its molar mass, get this, so forth and so on. So, for example, I know off the top of my head that water is 18.02. So if I take 4.18 times 18.02, it would equal the 7.53. But again, these are numbers that will be given to you on the exam. So, the first problem is an iron skillet weighing 1.63 kilograms is heated on a stove to 178 degrees. Suppose the skillet is cooled to room temperature of 21 degrees C. How much energy in joules must be removed to affect this cooling? And the specific heat of iron is 0.449 joules per gram degree C. Okay, so as always, the process is going to be that the mass given is 1.63 kilograms. There we go. I have a temperature of 178 degrees C. I have another temperature of 21 degrees C. And it tells me, but it does say specific heat, but just looking at the units of joules per gram degree C, this is S, because S is the one that's got grams in it, 0.449 joules per gram degree C. Okay, so because of the fact it has S in it, I have Q is equal to SM delta T. Okay, you'll notice that the S is in grams, the mass is in kilograms, so I need to take this to kilograms. So you simply multiply by 1,000 or move the decimal place 3 to the left, and that's 1,630 grams. Delta T is T final minus T initial, although I'll tell you I don't put a whole lot of stock into this, and I'll just tell you why in just a second. But basically it's 21 minus the 178. So this gives me a negative 157 degrees C. Okay, and so I'm basically ready to plug it in at this point. So Q is equal to 0.449 times my 1,630 times my negative 157. And when I multiply all three of those together, I get a negative 114,904 joules. And it does tell you that it wants the answer in joules. Now, I don't like to worry about the sign here in the delta T because sometimes we're going to be monitoring the system, which this one is system, and if that's the case, then it works. If this was the surroundings, then it would be the opposite way. So I like to ask myself, since the skillet is cooled, it's giving off its heat. So the system, which I can tell because if this and this are the same thing, then that's the system. If they're different things, that means one's the system and one's the surroundings. So I'm cooling the system down so that it makes it exothermic and therefore has a negative Q value. Okay. Now, calorimetry is carried out, a calorimeter is a device used to measure that heat that's absorbed or heat evolved during a chemical reaction, okay, or physical change. We have two different types. We have the cheap, easy kind, which is called the coffee cup calorimeter, and it's just simply two styrofoam cups stacked together, okay? And then sometimes you'll have a lid across this also. Whoops, there's the lid. You'll have a lid across this to keep the heat from escaping from the top. Scientifically, a more sophisticated and accurate way of measuring it is something called a bomb calorimeter. And this is a highly insulated box here with controls of things like the temperatures, a stirring motor to make sure the temperature is uniform throughout. I even have another insulation here, okay? And I can ignite something and burn something in the presence of oxygen. And then this is water, which is also an insulator. So this is a very highly detailed type of measurement device. Now, to determine the heat of reaction from the calorimeter data, okay, you want to find the heat for the given amount of substance, okay. You want to find the number of moles of that substance and then divide the heat by the number of moles. So the formula is that the heat of reaction, or delta H, is going to be Q, which is going to either be depending on what's given to you, SM delta T, or C delta T, divided by N, and N is the moles. Okay? And that's how you go about doing that. In the next video, we will work two examples of that.